AP Chemistry, and welcome to Chapter 9. This should be relatively short, just like the outline for Chapter 9 was relatively short, because we're only covering the first few sections in terms of what is considered in scope for AP Chem. And the vast majority of this is review. So, thinking back to Chapter 8, in Chapter 8 we took atomic structure and applied that to how to draw a Lewis structure, where a Lewis structure simply gives us the details about what is bonded to what, and whether that is a single, double, or triple bond, right? It also gives us in electronegativity the foundations for understanding whether or not a bond, right, is polar, right? Whether the relationship between two atoms is polar or not, right? In Chapter 9, we layer on VSEPR theory, which then gives us a three-dimensional picture of the molecules. Obviously, whether or not it's a picture sort of depends on how things work in your head. And like I emphasized last year, everybody's head sees things differently, right? If you are not very good at seeing things in 3 dimensions in your head, it may be beneficial to come by and actually build every single structure by hand with models and flip it around in your hands to feel it and touch it and be sure you really understand the 3-dimensional nature of each molecule. So anyway, VSEPR, valence shell electron pair repulsion theory, right? Which says that in the valence shell, because that's what most bonding deals with, right? The electron pairs will repel each other so that they are as far apart as possible in 3-dimensional space as they can get, right? So the balloon example, right, which, you're like, oh, balloons, I don't, and it seems very simple, right? But they do a great job of demonstrating what happens when one electron domain and another electron domain are trying to be as far apart as possible in 3 dimensions, right? And this represents our nucleus for the most part, right, where that is the central part to which everything is attached, and everything else is trying to be as far apart as possible, right? And balloons will naturally do that exact same thing, okay? Like it says in the notes, you do have to memorize this. There is the other version also on Power School. So whichever you choose, I don't care. You do have to memorize it in its entirety, though. So don't forget that electron domains, right, include, right, lone pairs and bonding groups, okay? And I do prefer the term bonding groups because if you say bonding pair, then you might be tempted to consider a double bond as 2 groups, right? But it's not, because again, when we talk about valence shell electron pair repulsion theory, we are talking about the arrangement of atoms and all electron domains for that matter in 3-dimensional space. So just because you have one atom double bonded to another atom, the point is that these 2 dots can still only be one arrangement one to the other, right? That's what we're trying to explain here with VSEPR theory. So just try to be thoughtful about that. So anyway, if we have 2 electron domains, our only option is linear, like it says in your book. If we have 3 electron domains, our overall geometry is always going to be trigonal planar, but if one of those happens to be a lone pair, then we end up with something that is bent, right? Where basically just one of those 3 groups is now a lone pair. So if I wanted to talk about molecular geometry, right, then this is all that would remain. Yes? Does it make sense? Okay. So if we have 4 groups, the overall electron geometry is tetrahedral, right? But if we have one lone pair, then we end up with something that is what? Right, a trigonal pyramid. If we have 2 lone pairs, we end up with something that is, right, bent. See, so if we're talking about 2 lone pairs, then all that remains is this. Then again, all we have is a molecule that is bent. Yes? All right. Moving on to a trigonal bipyramid electron geometry. Note that here, this is the first time where, note that here, one bond angle, right? One bond angle, one bond angle. Now we have 2 different bond angles, so where that lone pair goes matters, right? And your book goes into that. Where in the lone pair, because it belongs to one atom and is not being shared between 2 atoms, takes up more space closer to the central atom, right? Which then, when you read further to the section on orbital hybridization, right, because it's in an unhybridized orbital, right, that orbital is going to be necessarily closer to that central atom. So anyway, the point is that the lone pair will always take up more space. So it will go into the area that puts it farthest from other electron domains, right? Which is why the first lone pair will go in here, right? Because that puts it 90 degrees from two things, right, and 120 degrees from other things, right? Whereas if it went here, right, in that case, it would be 90 degrees from three things. Yes? Does that make sense? Okay. So here we have, if we had one lone pair, right, which would go here, we would be left with a seesaw. If we had two lone pairs, right, so now if we have two lone pairs, we'd put one here, and then thoughtfully we would try again to maximize space, right, so we'd put the other one here, and we would end up with our T-shape. And then if we had three lone pairs, right, so we would have to put one more, and we'd want to put it in a place that's as far away from everything else, right? So it would go there, which means that this is my resulting molecule, which is why we end up at linear, right? And in our octahedral, right, we only have 90-degree bond angles, but same principle applies, right? If we put one lone pair there, we end up with a square pyramid. And if we get a second lone pair, now, again, we're going to try to put it in a place where it's farthest from everything else, right? So that's when we're going to put that down here, right? And we end up with a square planar, right? And in turn, the words mean what they say, right? So square pyramid means square bottom pyramid, right? Square planar means square shaped, all in the same plane, right? So as long as we're paying attention to what we're saying and writing, that should help to steer us about whether or not that shape name makes sense for that molecule. Yes? All right. Bond angles in acetone. So this is the condensed formula for acetone. These two are what you're more likely to see on, say, the AP Chem exam, especially if you were asked to, say, determine bond angles or something like that, right? So this, in order to determine bond angles, step one is to, right, draw a Lewis structure. So again, we have more than one carbon, right? So then we understand, ding, 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 carbons are going to form our backbone, right? So let's go ahead and talk about this notation here, right? So this thing in parentheses, right, that tells us we have two of those, right, attached to this, right? So we have a C and an O, and we have CH3 groups attached to that, right? And we have an O up here, and we understand that carbons have to have 4 bonds, so we would do that and that. And these carbons each already have 4 bonds, because if there are 3 H's attached to them, right, then those are already 4 bonds, right? So does that make sense that in 2 seconds, if you understand that, you can come up with that? Likewise, this one says the same thing, right? This one says we have a CH3 group, and then we have a C, and we have an O, and we have another CH3 group. Yes? Does it make sense? All right. So anyway, here's our structure for acetone, and we would like to come up with the bond angles. So I just left it very broad. All right, so we would take a look at this central C first. Well, let's look at these outside. So these outside ones are equivalent, where we have a C bonded to this C, bonded to 3 H's, which means that this carbon has a bond angle of what? Right. These are 109.5, right? Likewise over here, 109.5, right? Thinking about this carbon, right? We have a carbon. How many electron domains? 3, right? So these bond angles are 120, because this one is trigonal planar, right? Then that's it. Yes. Does that make sense? Okay. So we're just going to take all these same principles, right? And we're just going to go one atom or one central atom at a time. Yeah. Does that make sense? Okay. All right. Polarity. So whether or not, so we talked about electronegativity as being the key determiner for polarity between 2 atoms, right? So if we want to talk about polarity of a molecule, right, step 1 is we must have a polar bond, right? And that's going to go back to 1, your Lewis structure, 2, your electronegativity tables, right? And then we would consider our VSEPR. Now, if it happens to be a diatomic molecule, obviously it's as simple as electronegativity. But if it's bigger than that, right, so for here, for example, right, the fact that there's a significant electronegativity difference tells you, yes, that is a polar molecule, right? But then we have to analyze our VSEPR. And I don't know of any more succinct way to say it, except that in order to be a polar molecule, 1, there must be polar bonds. 2, the atoms must be asymmetrically distributed about the central atom. Okay, so 1, it must have polar bonds. 2, the atoms must be asymmetrically distributed about the central atom, okay? So if we look here at CCl4, right, carbon and chlorine, definitely a polar bond, right? That's what this is telling you, right? In that all those bonds are polar, okay? But going back to what your book says, those vectors all cancel, right? It's in they're all pointing in opposite directions, right? Which means that there is no net dipole moment for CCl4, yes? And we can think of that as saying that there's no way for the positive part, which is the carbon, right? So this is like our positive part, right? To be separate from, right, these negative parts, right? Trying to think of it, imagining it as a magnet. If there's no way for this to align in a magnetic field, right, it can't have a dipole moment. Yes, does that make sense, right? Versus up here where we have NH3, right? Again, we have polar bonds. And note, again, the polarity is not just default positive is in the middle, right? It depends on what we're talking about, right? So here in this case with the hydrogens out here, right, the negative is actually this, right? The nitrogen in the middle. And now, because there is nothing up here, well, actually, what's up there, right? We have our lone pair taking up space, right? But there's no atom up there, which means that now we have a nitrogen end of the molecule and we have a hydrogen end of the molecule, which means that it's like this is my negative end, this is my positive end, and it can align in a magnetic field. Yes? Does that make sense? Okay. Here, BF3, same principle. We have very polar bonds, but again, all the dipoles cancel. This is a super duper excellent example to pay attention to because last year, when we just talked very broadly, right, typically we just labeled things that were symmetrical in nature nonpolar, right? So like this would just get a nonpolar label because of its shape. But then you would look at this one and say, oh, well, isn't that the same shape? And yes, indeed it is. But here is where we have to be a tiny bit more thoughtful. Here, the dipoles do not all cancel, right? Here we have 3 what is basically nonpolar bonds and 1 polar bond in that direction, right? Which means that even though the overall arrangement of atoms does not seem to be asymmetrical, there is that extra thing to think about, right? So if the bonded atoms are not all the same, we have to be more thoughtful, okay? Make sense? Okay. If the bonding atoms are not all the same, we have to be more thoughtful. All right, valence bond theory, right, which states this is the basic assumption for how bonding occurs, right? We have atom number 1, right, or atom A and atom B, and their valence shells or their valence orbitals, right? When they are infinitely, so this would actually continue out here. When they are infinitely far apart, their relative energy is 0, right? In that there is no attraction and no repulsion. As those valence shells get closer and closer, right, and they start to overlap, and that's once they overlap at the most ideal place, we call that a bond, yes? When the orbital overlap is ideal, when it has maximized the attractions and minimized the repulsions, because again, right, we have negative electrons, right? We have all of our core electrons, we have our positive nuclei, so there is a lot of opportunity for repulsion in addition to that mutually shared attraction to shared electrons, right? So all of those are at play. At one particular instance, right, the attractions are maximized, the repulsions are minimized, and we say that a bond forms. On the x-axis, that is our bond length. On the y-axis, right, that could be considered the magnitude of our bond energy. Yes? Magnitude of our bond energy. If, perchance, those atoms are forced any closer together, right, note that the energy goes up, right, and eventually becomes positive again, because at that point, right, repulsions start to be more important or more impactful than attractions. Yes, this is an important graph. It shows up on a lot of stuff. Make sure you understand it. All right, hybridization. So how do we explain the fact that valence shells overlap, right? But if we think about it, right, if an s orbital with its shape overlapped with another s orbital, right, sure, right, they would be directly apart from each other in space. But if we think about the arrangement of p orbitals in space, right, so p orbitals are aligned, so this figure doesn't really show it very well, but p orbitals are aligned on the x, y, and z axes respectively, right, 3 different p orbitals, right? That doesn't really explain a bond angle of 109.5, right, which sort of points in 4 opposite but equal directions, right? Oh, here they are. So that being the case, right, this hybridization theory is something that's layered onto the concept of valence bond theory, or valence orbital overlap, to sort of help explain, right, the shapes that we see and the bond angles that we see, right, which says that our valence, again, is composed of an s and 3 p orbitals, right, because that's what all bonding is, right, is the filling of those s and p subshells, right? So if we think about those as being our available orbitals, if we were to take an s and a singular p orbital and mix them together, we would get an sp hybrid orbital, right? If we took an s and 2 p's, we would get, oh, you guessed it, sp2 hybridization, right? So sp means we created 2 hybrid orbitals, right? sp2 means I created 3 hybrid orbitals, right? And finally, if I took all of my valence subshells and hybridized them, I would get 4 of these sp3 hybridized orbitals. Yes? Okay. Where sp, sp2, and sp3 is just a label for basically how many orbitals did we hybridize in order to come up with that, right? Important to note that sp3, which utilizes all of my p orbitals, means I have no remaining p orbitals in the valence shell of that central atom, right? Which means there is no potential for pi bonding in that scenario. Yes? No potential for pi bonding in an sp3 hybridized atom. All right, so here this is just a summary of the hybridization, and that is the extent to which you need to understand hybridization, by the way. If you look at the VSEPR table that's on PowerSchool, you'll see that it's just sort of, I believe I put the labels on there with the appropriate shapes, and there are very few things where I say this in chemistry, but it is one of the few things where you could just literally memorize what shapes it belongs to, and that would be sufficient. In addition to that little tidbit I said about sp3s don't have a spare p orbital for pi bonding. Okay. All right, so hybridization and multiple bonds, that's where... So hybridization theory also helps to explain the concept of multiple bonds, right? It's an understood observation that when we have multiple bonds, right, we often get things like resonance, okay, which means that we have delocalized electrons that are free to, that seemingly exist everywhere within the molecule, right? So that's one observation, which leads to things like equivalent bond lengths and strengths, right, which don't seem terribly logical at first, right? In addition, when we have multiple bonds, it fixes bond rotation, right? So hypothetically, if we think about a C and a C, and these are all H's, right? If everybody is singly bonded, it is understood that there is free rotation about this bond, right? As in that C and that C rotate freely about that bond one to another. It's also understood that once we put a double bond in there, right, that freedom of rotation goes away, right? And so the concept of sigma and pi bonding helps to put an explanation to that, right? So it's, again, just another layer that helps to explain the observations that we see, right? So once we put that double bond in there, it is understood that this molecule does not have free rotation about that carbon-carbon double bond, okay? So here, this is just trying to show you that when 2 atoms come together, right, that first bond is always called a sigma bond, right? If there are unused p orbitals, we can use those p orbitals as long as they align and they overlap to form pi bonds, right? Which is why you don't ever have a pi bond if there's not already a sigma bond, right? So that's often a trick question on your multiple choice section, right? And depending on how many of the p orbitals are left, 1 or 2, that's going to determine whether you can have a double bond or a triple bond, okay? And again, like I said, the fact that we have all those p orbitals that are available and overlap amongst the atoms, right, that's what leads to things like delocalization of electrons, because an electron pair or 2, right, can migrate through all of those available p orbitals. Yes? Does that make sense, right? So all of these things, all of these layers that get added on, right, sort of bookend each other and make sense together, which is why they're understood theories, right, for how bonding occurs in molecules at this point. Yes? Does that make sense? All right. Thank you for listening. Be good. Have a lovely day, and I will see you soon. Bye.